Okay, we've digressed from the original problem, obtaining an integral that should give us the surface area corresponding to a region specified in terms of limits on r and theta. We've mentioned that this can be extended to general functions u and v, or to general parameters u and v, where x, y, and z are functions of u and v. I'm going to return to the original question where the interpretation is that r and theta are the polar coordinates. So that this entire argument here expands, and again, after a miracle occurs, the miracle being what we've just seen, we conclude that the vector r sub r delta r is tangent to the surface r sub theta delta theta is tangent to the surface, and the integral of the magnitude of the cross product of these two tangent vectors is a surface area. Now, the vector function we're going to use as an example, this one has a very simple interpretation. In the x and y plane, we see that this is simply the equation, or for given r and letting theta go from 0 to 2 pi. This is just a circle in the xy plane, and as long as r isn't bigger than a, our k coordinate, our z coordinate, is related to the x and y coordinates by the simple relationship that you can verify yourself: x squared plus y squared plus z squared equals a squared. Now here's your x, here's your y, and here's your z. If I do this squared plus this squared, I get r squared times cosine squared theta plus sine squared theta, which is just r squared. So x squared plus y squared equals r squared. Add that to the square of this, you get you'll be adding r squared to a squared minus r squared, which will give you a squared. So this is a sphere, radius a, center at the origin. We know the formula for that surface area, and we've derived it by other means. We're going to use this relationship now with this parameterization of that sphere in order to obtain the same result and at least make plausible this formula. Now, implicitly, this function is defined for 0 less than or equal to r less than or equal to a, and 0 less than or equal to theta less than or equal to 2 pi. That defines every point around a circle of radius, or within a circle of radius a, centered at the origin, and our resulting values of the k component, our z component of the r vector, raises us up to the surface of the sphere. Now let's be a little more specific with these limits with a positive value of k here. This is the hemisphere of radius A center origin above the xy plane. If our little miracles have given us a correct formula, it should be easy to find the r and theta derivatives of this function, find their cross product, find the magnitude of the cross product, and integrate that with respect to r and theta with these values, with these ranges of r and theta. So, what's r sub r? Straightforward. We simply get cosine theta I plus sine theta j, and then the derivative of this with respect to r is going to be negative 2r over 2 times the square root, etc., which it is then simply negative r over the square root of a squared minus r squared times k. Our theta derivative is even simpler. First place, there's no theta dependence on k. There's no theta dependence in the z component, the multiple of k, so that's going to be 0 with respect to theta. Derivative of r cosine theta is negative r sine theta times I plus r cosine theta times j. And there's nothing particularly intimidating about these expressions or the idea of taking their cross product. So we'll continue with those details in the next clip, but we see that having found r sub r and r sub theta, all we have to do is take the cross product, find the magnitude, maybe just a little messy but not particularly difficult at all, and then integrate that with respect to r and theta, and hopefully what we get when we do the magnitude of the cross product will be an expression that we can easily integrate with respect to r and theta.